Wonderful. So it's great to be at TI again and actually to have a keynote. So I'll be talking to you about for the next 30 minutes about big data and my ideas of what's going to be happening next. First, I'm a medical doctor, so I usually have to start with my conflicts of interest. I have just a few. Suffice it to say, at the top of the list, I've started a bunch of companies. I consult for a bunch of companies. You might not want to believe another word I say over the next 30 minutes. I wouldn't blame you. I'm most proud of the bottom right of this slide. Those are all the companies started by my students. More than half my graduate students now start companies, even if they go into academia. And they do this with the most amazing platform in the world. And it's simply data. And it's often big data. It's often open big data. So I'm going to show you how they do it. I'm going to show you how I do it, and maybe I'll convince you this is the most amazing time for biomedical entrepreneurship and innovation. In my lab, we do have a saying that if you want to change the world, you can't just keep writing papers about it. You actually have to file some IP, and if no one licenses that intellectual property, it's up to you to start the company. So that's what we do. So let's get started. We're obviously in this new era of big data. My favorite example of this is the cover of The Economist magazine about 5 years ago, where this guy's collecting ones and zeros with the umbrella. And oh, by the way, so how many of you are on Twitter right now, actually, in the room here? So there's a handful. My Twitter handle is there, and I'm actually live tweeting my own talk, so you can actually follow me for extra features on each slide. So if you follow me, you'll see extra links to articles. There's a link to this Economist article. This is the article from 5 years ago that announced that the human species generates 2 zettabytes of data every year. If you forget your metric prefixes, it goes kilo, mega, giga, tera, peta, exa, zettabyte. And of course, the following year it's 4 zettabytes, and 8 zettabytes, and 16 zettabytes of data. I'll be the first to admit, most of these zettabytes of data are YouTube videos of kittens playing with pianos and yarn. Entertainment value, perhaps no scientific value, but there are scientific data sets into zettabytes. For example, the Large Hadron Collider in Europe generated petabytes of data to help those scientists find out new subatomic particles. By the way, all that data is open. But a better example is NASA. So NASA announced about 2 years ago that with the new orbiting telescopes that they're planning, that by the end of this decade, they think they might be able to generate an exabyte of data every day. In terms of pictures, an exabyte of data every day. Now, there's something interesting about NASA's exabytes already. NASA already admits they generate so many pictures of the sky, there are not enough astronomers on this planet to look at all the pictures, right? So how do they solve this problem? Well, they have something set up called Galaxy Zoo. You can go there, you can take a test, and then you, as a citizen scientist, become the person who actually says, this is a star, this is a galaxy. It's actually up to you. So it's a telling story from NASA that if you have too much scientific data, you need to open up your data to a new crowd, a new audience to help you get to the scientific discoveries you need to, right? Crowdsourcing and citizen scientists. And of course, I'm going to tell you we're there in life science research as well. And we're there because of gadgets like this. Now, I could have shown you a sequencer with blinking lights from Illumina. I could have showed you a mass spectrometer. I could have showed you a proteomics setup. I love showing these. These are gene chips from a company called Affymetrix, actually not too far from here, in Santa Clara, right, kind of near Intel. This is how I got my start about 18 years ago. These were priceless chips. You put a sample of DNA or RNA from cancer or animal models or cell lines, and you get a readout of every gene in the genome. You just get a measurement, how much of all those recipes are getting cooked. And actually, they were priceless when I got started, and now they're so cheap, I carry one in every suit. So this is what they actually look like. I'm holding one in my hand here. Big data comes from little packages just like this. And it's amazing, a couple $100, you get a readout of the whole genome. In fact, we get tired of measuring them one by one, so now we have a 96-well plate format. That is so cheap, I carry that in my bag, and you can see that in my hands here. And then you get tired of measuring them 96 at a time, and now there's a 384-well plate format. And that is so cheap, I carry that in my bag, and you see it in my hands here. I cannot more clearly illustrate exponential growth in biomedical data than to show you these plates, right? Over 18 years. And we don't even use this one anymore because we moved on to something called RNA-seq, and this company doesn't even exist anymore, right? They got acquired by Thermo last year, right? This is how fast we're just generating measurements in biomedicine. today. So many measurements. And what happened is all the scientists started using these chips. It's not even a big deal to use these. And so everyone started writing scientific papers. Here's a paper with a list of genes on the, different genes in cancer or heart failure or diabetes. And everyone had these papers. Early 2000, 2001, 2002, everyone started submitting these papers. And the scientific journals, it started with them, they said, hold on a second, we're getting too many papers with these gene chips. No more scientific publications with these gene chips. That's it.